Okay, hopefully I should be live. The audio level should be fine as well. I don't see any feed. What is this? Hello. Oh, look, I guess I'm lagging. Oof, what is this? I guess I'm lagging. Most probably. Yeah, the Wi-Fi is not the best, so I expect that. Yeah, so am so I am lagging. Oh, now there's you know what? Anyways, let's move on and let me check here and solve some problems. Okay. Oh, before this, I do want to check um Codefest. Codefest 2026. Let's see. Hmm. Okay, so they will be asking DP and graph problems and advanced data structures. Okay, I will be going for this route, this track. Hmm. Prelims is on 31st Jan. Okay. Ooh, okay, so this just motivated me to solve more DP problems. Let's check their Discord and WhatsApp. Open. Okay. Okay, only admins can see all members. Hmm. Hmm. Okay. Korish Balega is in here. Okay. Where is the invite? Hello. Okay, I have been added. Yeah. Cool. Just a minute, I will be back. Victor Black.
From tomorrow, 8 days.
Ayan, Okay, let's check their Discord. Okay, let's register. Okay, oh, I have to make a resume. Okay, great. Well, no one's going to see this, but yeah, hmm, never mind. Um, hmm, What is a transcript link? What is a transcript link? Ro-
periods
Why do you need all of this? Academic transcripts? Hmm,
में एक्स्ट्रा लॉन्ग डेज यानी लीकेज की
ro-
एक्स्ट्रा टेंशन इसलिए
Okay, cool. Cash.
The transcript is one essential document that you need for your application process. And in terms of requirements, certain schools will always require the official for application process, while some schools will require the unofficial document. Official
ro-
as or bachelor's, okay? While unofficial transcript is probably the document you got from your school website, or maybe the correlation of your results, the compilation of your results, and that has been stamped by your school. So that is like the difference between officials and unofficial transcript. Now let's talk about application process. Like the transcript is one essential document that you need for your application process. And in terms of requirements, certain schools will always require the official for application process, while some schools will require the unofficial document. So make sure you know the one that the school you're applying to is asking for. For official document, the official transcript, when I mean official document, I'm talking about the official transcript. When you're requesting for the official transcript, you want to make sure that you send the
ro-
Welcome. In this tutorial video, we will explain what a transcript is, how to understand what is on it, and answer some of your most frequently asked questions.
In Section 2, we will cover what information is on a transcript. This section will include more information about GPA, academic standing, and a transcript is your permanent academic record at Alexander College. A transcript can be used for two purposes: for you to have a centralized record of your own academic performance, and for you to be able to share a record of your academic performance with other institutions or organizations. For example, transcripts are often needed when you are applying to post-secondary institutions or posts on a transcript. Let us transcript Unofficial transcripts can be downloaded directly by you from your MyAC student portal using a computer or mobile. The function for distinctions between an unofficial and used for different purposes. There are two major distinctions between an unofficial and official transcript. These are the function, for example, what the document is used for, and the security features. Unofficial transcripts can be downloaded directly by you from your MyAC student portal using a computer or unofficial transcripts can be downloaded directly by you from your MyAC student portal using a computer or mobile device. This document does not include official letterhead or security features, so it cannot be used for official purposes such as applying for admission to a post-secondary institution. An unofficial transcript also contains information such as your level of study and academic standing, which are for your information only and do not appear on the official transcript. You can see an example of an unofficial transcript here on the left. By contrast, official transcripts, shown on your right, cannot be downloaded but must be ordered directly from the Office of the Registrar. To learn more about how to order your official transcript, see our tutorial video here. Official transcripts are printed on a special tamper-proof security paper and issued from the registrar directly to the student or receiving institution in a sealed envelope. Some post-secondary institutions will accept an official transcript only if it is mailed directly from the sending institution, and some will accept an official transcript submitted by a student as long as the envelope maintains its original seal. If you are unsure of the policy at the institution you are applying to, please ask before ordering.
Section 2. What information is on a transcript? Now that we have explained the differences between an unofficial and official transcript, let us go over each document in more detail. First, we will look at a sample of an unofficial transcript. You will see the title of the document, Unofficial Record, and the date that you have downloaded the document. Next, you will see your current level of study. All programs at Alexander College are classified as undergraduate level. So the level of studies, this will be in Good Act 1.5, your legal name, and your date of birth. The program to which your current grades have been submitted by faculty. After that, you will see your current program. This is the program to which you are currently admitted. This section of your unofficial transcript also displays your personal identifying information, including your student ID number, your legal name, and your date of birth. To follow, you will see a record of each term during which you were registered. Ask questions. Finally, let us review some of your
Other institution. Why is the transfer credit not showing on
transcript at a minimum of classes you wish to by your course instructor. It usually takes
Where is academic records? Okay, so this is a application form for transcript. To This is so dumb. Why do you need a transcript? They only need the username. Hmm. Twenty-third. Okay, so it's a Tuesday. Hmm. Will participate in this. Anyways, we'll look at this later. Yeah, let's solve some KP problems. But regular expression matching. Let's solve this daily problem first. And before that, I need to bring my charger first. So fade to black. Okay. Delete columns to make sorted. Given an array of n strings, STR is all of the same length. The strings can be arranged such that there is one on each line, making a grid. A, B, C, B, C, E, C, A, E. The strings can be arranged such that there is one on each line, making a grid. What does this mean? You want to delete the columns that are not sorted lexicographically. In the above example, column 0, ABC, okay, and second column, CEE, are sorted, while column 1, BCA, is not. So you would delete column 1. Return the number of columns that you will delete. Okay. Hmm. Okay, so first you need to find the minimum length and the maximum length of the individual strings, right? str and strs, just calculate int n equal to strs dot length int min int max min equal to math dot min of str dot max. Do what is max? Math dot max str dot um okay, so count equal to max minus min. These many columns you have to for sure delete, right? Now for int I equal to 0, I less than minimum I plus plus. iterate this many amount of times on all the characters. For str and strs, check the 0th character. If str dot char at, wait, this needs to be int j equal to 0, j less than min minus 1, j plus plus. No, this will be n minus 1. Right, wait. This is the character I'm looking at, and skrs of j, yeah, this makes sense, should be equal to, not equal to, it should be less than or equal to, right? Now, how do I calculate this? By doing this. And similarly, this, but this will be j plus 1. If, oops, I mean, if this is greater than count plus plus, count plus plus, and then break as well. And then the return count. Oh, oh, this needs to be initialized int count. Okay. Let's check though. What should we do? Will this pass all the test cases? Just wanted to check. Yeah, everything's working. All the levels are good. Yeah, I knew it. But the max length will have some characters, right? The strings can be arranged such that there is one or on each line, making a grid. Okay, so I don't need to worry about this case. I can directly initialize count to 0. Yeah, that's what they have done here. int count equal to 0. I can call this as R and this as column. So it's just that I need to do this. And this will be R minus 1. That's it, right? Hmm, Yeah, these are the columns, right? Yeah, makes sense. Perfect. Okay. Hmm. Let's solve that problem. Regular expression matching. Regular expression matching. Given an input string S and a pattern P. Okay. Is this a pattern matching problem? Let's see. Implement regular expression matching with support for this and this where this matches any single character. This matches 0 or more of the preceding elements. Match a single character, then match any characters. Hmm. Okay, so we have a couple of conditions. You're right. We send S, we send P. And what else do we send? We send I and J, which starts from 0, 0. And int this dot n or s length equal to s dot length and this is p length int s length and p length. Public boolean dfs, just copy this, int I, int j, int j dfs, just copy this, int I, int j. Okay, so what do we have here? I mean, what are the base conditions? If at any point we go out of bounds, that means we have found the correct string. Right, we'll come back to this later. Now, we have couple of choices. If let's first get the characters. S char s dot char at I e dot char at j s dot s char equal to p char. We are good and we move ahead, right? And dfs of sp I plus 1 j plus 1 return true. Else if s char, now P char equal to dot and dfs of s I plus no s. This will be only once j plus 1. Only a single character match. Return true. Else if p char equal to star then and s p I plus 1 but j remains the same. If this is true, return true. Otherwise return false. Oh, if this cannot be returning to a single string. If I is reached and j equal to p length, then return true. If and this is true, then return false. Yup. Oh yeah, this star case fails. Then here we need to check if p dot char at j equal to this. If this is true, then return true, else return false. Yeah, we should be good now. God damn it. Oh yeah, because j can be out of bounds. Okay, so write a different condition. If this is out of bounds, this is this, then return true, otherwise return false. Else if j is equal to p length, else if if then return false. This should be like this. Okay, please. That's it, right? Okay, let's see if this works or not. Will this pass all the test cases? Yes, right. Obviously, oh, why not? Star matches 0 or more of the preceding elements. If if we ever encounter this, just directly return true. Just directly return true, right? If we ever encounter this, directly return true. We don't need to check anything else. Now we can say that if I equal to s length or this. Now if any one of them reaches, it's definitely return false. If this yeah, we can also reduce this by doing this. So remove this and we should be good. That's it. Let's see. Like test pass. Wait, did I? Regular. Hmm, damn it. What? Oh, of the preceding elements means 0 or more of the. Therefore, by repeating a Okay, so this only matches the preceding elements. And okay, so it has no impact on the future, but it has an impact on the past. So it should be like this. If we ever reach this, return to hmm.
Do you know what's the future? Hey everyone, welcome back, and let's write some more neat code today. So today let's solve a pretty hard problem, regular expression matching. So we are given an input string S and a pattern or a regular expression P, and we want to implement regular expression matching. And these are the two special characters that we're gonna have to worry about, a period and a star. So the stars, or so the period will match to any particular character, and the star basically means that any character that comes before it can be repeated 0 times, or it can be repeated infinite times. For it can be repeated 0. Star basically means that any character that comes before it can be repeated 0 times, or it can be repeated infinite times, right? So it can be repeated as many times as it needs to be. And the match or the pattern has to
Oh.
cover the entire input string. So it has to match the full input string. So one example is, let's say, so these are the special characters we worry about, right? The period and the star. If we don't have either of them, then it's
Okay. Now I understood what the star means. Matches 0 or more of the preceding element.
basically string matching, right? So we see in this example, we have two A's, right? That's one input string and a single A. So basically, do these strings match each other? They don't match each other. So we have to return false, meaning that the input string S does not match this regular expression. And remember, it's only going to be our regular expression which possibly has the star or possibly has the period. Now imagine instead if our pattern was A period. So in that case, we would compare it to the string double A, and we would see that yes, they do match, because remember, the period can be any character. So we could say, okay, well, given this pattern, this could be double A, so it would match this input string. What if we were checking, does it match this input string AB? In that case, it would also match, because this period could
Okay,
then turn
period.
into
If there's a
AB, so it
period.
would be AB, and these two match each other. But of course, if we had A period period, checking if it matches double A, it doesn't, because they're not even the same length. This has 3, this has 2. There's no way we could put any characters for these two periods that would match double A. And what about this second example? Let's say the input string is double A and the pattern is A star. So what this star means is A star. So A star basically means that the element that comes before this A could be repeated multiple times or 0 times. So the possible strings that this pattern could match to could be an empty string, because this character could be repeated 0 times, right? So empty string, this character could be repeated once, so a single A. This character could be repeated twice, so double A. This character could be repeated 3 times, so triple A, and so on, right? We could repeat this A infinite number of times. But if you take a look at our input string, we're only checking, does it match double A? Of course it does, right? We just repeat the A twice. So in this case, we return true. A third example, so let's say our input string is AB. This dot star means is we could have a string that's empty, right? Repeating the dot 0 times, so empty string. We could repeat the dot once, so dot, let's say this, right, double dot is what we're looking for. We're checking, does this be? So that you can see that there's comes from the star to deal with, right? The complexity really mainly comes from the star. The dot isn't so difficult, right? But the star makes things interesting. From the star, the dot isn't
Hmm.
So let's just try to brute. force this. Let's look at one example, this example. Let's say this is our string S and this is our pattern A star. So as you know, the star is really where the complexity comes from. So let's make a decision tree. Let's brute force this. So this is the string we're trying to match to. This is our pattern A star. We know, so we're first going to look at the first A and then we're going to look at the first character of this. Now that comes after it. So this could be repeated 0 times or more times, right? So let's brute force this. We know we have a choice. Are we going to repeat the A at least once or are we going to repeat it 0 times? If we repeat it 0 times, then we end up with an empty string, right? If we repeat it once, we end up with a single A. Now, clearly we want the single A because it matches this, right? And if we decided to have an empty string, meaning we want this star to, and this character A to repeat 0 times, then we would have to move to this position, right? And there clearly isn't any character here. Maybe there would be a B, maybe this character A to repeat 0 times, right? If we repeat it once, we end up with a single A, 0, right? So let's brute force this. We know we have a choice. Are we going to repeat the A at least once or are we going to repeat it 0 times? If we repeat it 0 times, then we end up with an empty string, right? If we repeat it once, we end up with a single A. Now, clearly we want the single A because it matches this, right? And if we decided to have an empty string, meaning we want this star to, and this character A to repeat 0 times, then we would have to move to this position, right? And there clearly isn't any character here. Maybe there would be a B, maybe there would be an A, but there's clearly nothing there. So this decision is going to stop, right? We cannot go any farther. All we can do here is an empty string. But it's okay because we ended up matching with this A when we were on this path, right? So now the character we're looking to match in the input string is this single A. So now again, we have a choice. Are we going to repeat the star? Like in this spot, we repeated the star. In this, we didn't repeat the star. Now, again, we have that choice. Are we going to repeat the star or are we not going to repeat the star? If we don't repeat the star, we're going to end up with a single A, and then we're going to have to be shifted over to this position, meaning we cannot use the star anymore. So we're going to stop, right? This is going to be our string, a single A. But you can see in our input string was a double A. So really, our other decision where we do repeat the star.
Just a minute, I will be back soon. Fake to black.
At least one more time is going to lead us to double A. And that's good because now we have the second A, meaning we matched this second A, right? So now in reality, we have matched the input string. But just to show you, in theory, we could keep going. We could decide not to use the star anymore, right? We would be shifted to that position, and in which case our ending string would just be double A. Or we could use the star one more time, meaning we'd get triple A. But then, of course, you can see we're even bigger than the input string that we wanted to match, so we stop. But we see that we did end up finding the result. Since we found the result, right, we found the input string, that means that these do match, right? So we would return true because the input string matches the regular expression. But as you can see, we're doing a decision tree. This is not exactly going to be super efficient, right? How many decisions are we going to have? Well, anytime we get to a star, we're going to have 2 different decisions. How many times can we repeat that decision? It's going to be n, where n is the input string S. So clearly you can tell this is not super efficient. But in case you haven't noticed, this is a dynamic programming problem. And if we take this and we implement a cache, then we can get this time complexity down to n squared. Or in other words, really, we're getting it down to n times m, where n is the length of the input string and m is the length of the pattern. And this is if we do the top-down memoization with a cache. We can also do the actual bottom-up dynamic programming solution, so the bottom-up dynamic programming solution. And both of these actually have the same time complexity. So I'm going to show you the top-down coding solution. But once you know the top-down solution, getting the I'm going to use, so let's say this is our input string, and to tell us where we're at in the input string, 2 choices. So I'm going to draw our decision tree. The star, meaning we use the character at least once, we're going to get a C, right? We're going to repeat the C just once. If we don't do that, we're going to get an empty string. So I'll just draw this dash for empty string. Now you can see we have a C, but the first character of our input string is A. So really what we want to do is not use this C any times, meaning we do not want to use the star. We don't want to repeat C even a single time. So the decision we want is not this decision, but this is the path that's going to lead us to the correct answer. So what am I going to do with this J pointer? I'm going to shift J. So I'm going to shift J over here, right? So notice what we just did. In this path where we do not use the star, right? We didn't use the star. What did we do? We ended up shifting J by 2. So we took J and then added 2 to it. That's very important because anytime we choose not to use the star, we're going to take our pointer where it's at and then shift it twice because we're shifting 1 to get to the next character, but also look at the star. We don't use this decision. What we did is we left I the exact code. So again, we have a decision to make. So one decision is we use the star at least once. The other decision is we do not use the star at all. So if we use the star once, we'll get a string of A. If we don't use the star, again, we'll end up with an empty list or an empty string. So remember when we used the star over here, we got a C that didn't match the A, but now we actually have an A that exactly matches the character over here, right? But what about this path, right? Right now we have an empty string. Is this path going to lead us to the correct answer? Well, the only way to find out would be to continue on this decision tree, right? Making decisions and stuff, but I'm not going to show that because it's going to get pretty messy. And you can tell by looking at the string, since we chose this path, we would have to leave I as it is and we have to add 2 to J. So I
would stay here, J would be moved over here, and then you see the pattern left at this point is just B. Does that match the input string S? It definitely does. Continue on this path. A, exactly what we wanted to do, right? So what are we going to do with I? Well, we're allowed to shift it by 1 now. So we're going to take I and move it over here, right? We already matched this character. We don't really need to match it again, but we do need to match the remaining string of S, A and B. What about J? Well, J can stay the same because we used the star once. We repeated this A once. Now we can continue to repeat it, or we can repeat it 0 times. And we can make that decision by leaving J exactly where it is. So when we go down this path, when we actually use the star, what we're going to do is add 1 to I, but leave J exactly as it is. And this is important too. These two things are important because this is exactly what I'm going to do when I write the code. So since we're still at J and there still is a star that comes after it, we again have 2 choices. So we can choose again to repeat this A or not to repeat A. Then we're gonna have a single A, and then meaning we're not gonna use this anymore, and then we're gonna have a B that comes after it, right? And you can tell AB by itself does not match the entire input string, right? This is exactly what, and J is over there, so what we had before, right? But in this case, as we usually do when we don't use the star, what we're gonna end up doing is taking I, leaving it where it is, because we know we didn't match this character right now, but we're gonna take J and add 2 to it. And since we add 2 to J, that means we have to shift it after. There's no star that comes after it, right? So we actually don't have a choice other B. We don't have a choice because single choice right now. I equal take I. If we take our I and then shift it over here, so I'm just gonna make just a single A, right? Let's say our index of character. So showed a second ago out of bounds and J is out of bounds. That means we have found our solution. That means we were able to match the pattern to the string so we can return true. But as I showed you, if I is not out of bounds but J is out of bounds, we have some string in S that we haven't matched and there's no way we're gonna be able to match it, so we have to return false. So these are our 2 basic cases. Notice that given these 2 cases, it's still possible that I could be out of bounds, right? I technically could be out of bounds and neither of these return statements would execute, right? Because this needs I and J to be out of bounds. So we would pass this and we would pass this and I could still be out of bounds, but I'm gonna show you how I'm gonna handle that right now. So the first thing we wanna check is there a match between the first character? So is there a match between S of I and P of J? And the other thing we could check technically, right, or check this. And since we know I could technically be out of bounds, before we even check this, we have to confirm that I is in bounds. So I is less than the length of S. So strictly less than, not less than equal. So if these conditions are satisfied, that means the first character of each string matches exactly. The reason I'm putting this in a variable is we're gonna have to repeat it a couple times in the following code. So the first thing I wanna check is, does the following character in the pattern string, so P of J plus 1, does it match the star? Is it a star? And the reason I'm checking this first is because the star has the highest precedence, and I'm checking J plus 1 because we know the pattern, the first character in the pattern string is never going to be a star. And since I'm checking P of J plus 1, I have to first check that J plus 1 is in bounds. So I have to check that it's less than the length of P. So if this is true, that means we're gonna have to take care of this star, right? And we remember when we encounter a star, we have 2 choices. So I'm gonna do a recursive call, right? That first search, the first choice we have is don't use the star, right? If we don't use the star, we leave I as it is and we take J and add 2 to it, right? That's 1. Now, we know we have 2 choices. If either of them evaluates to true, then we can return true, right? We're brute forcing this right now. So the other decision we have is use the star, right? So if we use the star, that means we can take I and add 1 to it, and we can leave J where it is. But remember, we can only use the star if there's a match between the first character, right? The first 2 characters, right? Because we only want to use the star if there happens to be a match. So really here, we're checking if there's a match, and this whole thing, this recursive call evaluates to true, right? So I'm gonna wrap this in parentheses. So basically what I'm saying is these are our 2 choices. This is one recursive call and this is another recursive call. If either of these evaluates to true, then we can return true. And that's what I'm doing basically by putting these on the same line. So I don't know the best way to format this. Maybe this is somewhat readable. So if either of these is true, we're going to end up returning true. If neither of them is true, we're going to return false. So this by itself, these 3 lines of code handles that star for us. Now, if this isn't true, meaning we don't have a star character, then we're looking just for a simple match, right? So we can just check if the 2 characters match, then what are we going to do? Well, remember, we can then increment I by 1 and we can increment J by 1.
Your game doesn't play the way it should.
Result of that. Now, if there's not a star and the characters don't match, in that case, it's simple, right? Then we can just return false, meaning that this string will never match the pattern. So then we return false. And this is the brute force solution. It's actually as simple as that. So let's return it and let me show you how inefficient it is right now. So we can call our depth first search starting at 0 in both of the strings. Oops, I had a syntax error. So we had double equal over here. We have to put double equal over here. Oops, and one last thing, when you have multi-line stuff in Python, you have to wrap it all in parentheses, so I'm just going to wrap this entire thing in parentheses. Hopefully it's still readable. And a third bug, so I don't know why I checked if J is out of bounds of string S when J refers to the index of string P. So sorry about these bugs, but okay, so this time it finally worked. You can see it's not super efficient, right? It took about, I think this is 1.3 seconds, and it was 11%. So we did the brute force solution, but look, I forgot to do the memoization, right? So let's actually do the caching now and make this efficient. So I'm going to create a cache. We did the brute force solution, but look, I forgot to do the memoization, right? So let's add 0.3 seconds, and it was 11%. So I'm going to create a cache.
Okay, I understand this. So the main trick was the star. The tricky part was star. Rest was pretty simple, I would say. Like, I didn't understand what this line meant. So, yeah. So, we have a boolean named match. Now, if I is within bounds S length, and if this is within bounds, and what do we have here? We have to check if S char equal to P char, and if P char equal to this, yeah, this, then it is a match, right? We check some condition here, but let's check this condition as well. If match is true, then return DFS of SP I plus 1 and J plus 1. If our next character, if is the if P char if J plus 1 is within bounds and is P dot char at J plus 1 is equal to this star, then we basically have two decisions to make. What is it? First one is to call TFS SP. This will be to use the same character, right? So I plus no I plus 1 and J plus 2. SP, and this will be I plus 1. Wait. We use the same character, right? So J will be at that position and I will increment. If we don't want to use the same character, then we move on. But here we do need to check if it is a match or not. Okay. Hmm. If we don't want to use this previous character, okay, we can use it 0 amounts of time as well, right? So if we want to skip, this will be at I only. This is skip. This this is take condition. Yeah, this makes sense. Now, okay, just initialize the DP, right? Let's keep it boolean of size s length and p length, and into dp it's not int, It's Boolean. If dp of I comma j is brother is not equal to null, then return this. Otherwise, store it in here. Otherwise, store it in here. Otherwise, store it in here. That's it, right? Hmm. Okay, I should be good. Uh,
It's going, ij has already been added to our cache. If it has, then we can return it, right? So this is going to basically not have, so instead of returning this right away, you can see down here, I'm going to actually take this and add it to the cache. So at index ij, I'm going to put the value that this returns to. And after that, after we add it to the cache, then I'm going to return it. And I'm going to do the exact same thing down here. So adding this to the cache, and then we can take this and return it. So all we're doing right now is caching the work that we do, so we don't have to repeat it. Lastly, down here, we can say in the cache, add false, and then return false. So basically by just adding like 4 or 5 lines of code, we've added the caching element to this function. It was pretty easy. So taking the brute force to the optimal solution was actually pretty easy. And look at the result. Look how much faster this is. 44 milliseconds, 81%. So we
oh, this, oh my god. It should be or here. That's it, right? That's the only problem. Yeah. Should I just write this equal to s length return false?
actually didn't even
This will throw an error. So this will be SLN.
need to do the bottom-up dynamic programming solution, right? And this, I will be honest with you, is not the prettiest way to write this code. I've seen solutions that are a lot better than this, but I really hope that you at least were able to understand what we're doing, right? The meat of the work is done in this call, right? Basically, these 2 lines of code are the work that we're doing, right? This is where we're handling the star case. And you can see it's actually not that difficult, right? All we're doing is I stays the same, j added 2, or I plus 1, j stays the same, right? And you understand why we're doing it like that from the picture that I drew. But I encourage you to do the dynamic programming solution. I'll probably link the code for that in the description. And I hope this was helpful. If you enjoyed, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon.
If you are an aspiring
The reason behind your overthinking.
If you're still typing your coding prompts, you're
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve a very popular problem and probably one of my favorite problems of all time. It's Jump Game. So this is a very popular dynamic programming problem, but it can also be solved in a greedy way. I'm going to show you both solutions, and then we're going to code up the greedy solution, and it's very little code, so that's the good thing. But it's a pretty clever problem, so let's dive in.
Let's mark this off and actually solve this problem. Defy Jump Game. Okay. Jump game. You are given an integer array nums. You are initially positioned at the array's first index, and each element in the array represents your maximum jump length. Okay. Your initial position at the and at the at that position. Return true if you can reach the last index, or false otherwise. This is 1, 2. You're at you're here, then 1, then 1. You are at the last index. Jump 1 step from index 0 to 1. Okay. And your maximum jump length. Okay. So I have the okay, so when I move I, I have this number 2. So I have two possibilities, either I jump here or I jump here. 3, so 1, 2, 3. But I can jump here or here as well, but this will lead me to here, which is not the end. Okay. Hmm. And this dot n equal to nums dot length. I think I have a solution in mind, but let's see. Public boolean jump. This is int nums. This is the current position. If I equal to n minus 1, return true. If I is greater than equal to n, then return false. Now, if it is going beyond that as well, then return true, right? Because that's the maximum you can go. We need to be within that range. Okay. For int I equal to no, j equal to I, j less than nums of I, like this will be I plus this j plus plus. We call the jump. Jump will be nums and j. This can be 0 as well. If this is 0. So this will be this index, current index plus 0. So it will be same. So now it will never execute if this is equal to 0. Its nums are equal to 0. So I should jump to the next index. Okay, this is correct, but but, I need to memorize this. So Boolean dp new, oh wait, dp equal to new Boolean of size n. This will be capital P. Give test cases for this question. Raj. Type the entire test case out so that I can copy it and paste it. Delete one. Only give test cases. The constraints are high, so so construct test cases that are very large within constraints. Use variety of numbers. Yeah, that is true. This is often square.
into it. So we're given an array of non-negative numbers, so all
You know what? I think I will check. Um, I think I will check what? Will I check? By submitting this code. Yeah. It might give a TLE, but let's see. A wrong answer. Not a TLE though. A wrong answer. We have 2. This should return true, yeah. Why is it returning false? This should be equal to, shouldn't it? I plus terms of this. But anyways, Fix this record save code. Oh, this should be. Oh, if this is true, just return true. This will be J, right? No, I. Okay, from ith position it is possible. That's why. One minus one and I plus minus I. This will be false. As soon as we get to know that it is possible to jump from this ith index till the end, we return store that as true and return it as true. We will just pass all the test cases. Because it did pass this test case, but okay. Let's see. It did take a lot of time, but yeah, it was definitely accepted. Which oh wait, I need to create a folder. Hmm. Hmm. So let's think of the greedy approach now. Right. So if we are at 2, you will greedily jump now. Let's think of it like this. We cannot think from the end, right? That is when we reach here. We say that we have reached here, but can this index say that we have reached here? Can this index say we have reached here? Let's see the
We're going to be
greedy
0 or
approach.
positive, and we're initially positioned at the first index of the array. So for example, in this input array, we're positioned at the first index or the 0th index, right? The first position. So this is where we're going to start. We're going to start in this position. And so for every value in the array, for every element, the number itself, for example, number 2 in the first position, represents the max jump length that we can perform at every single position. Basically what that means is from this first position, we can only do a max jump of 2, meaning our max jump can only get us to this position, right? And another example, from here, since this is a 1, this is a 3, the max jump we can do is a 3, meaning we can reach the end position, the 4, from here, right? Because we can do a jump of length 3. Given all of that, given that we're positioned here and that every value represents the jump size, we are only asked, can we reach the last index? So starting from here, given these jump values, are we able to reach the destination, which is the last value in the array? So in this first example, the answer is yes. So we return true because yes, we can reach this position. How can we do it? Well, we start here, so we can do a jump of length 2, or we can do a jump of length 1, right? We don't have to do the max jump length. We can choose to do one jump. So then let's say we're at the second position now, right? So now we're at 3. We can either do here, meaning we're at the last position, right? We're at the last position. Therefore, we did reach the end. Therefore, we can reach the end. So we return true. Okay, so let's look at a different example. Let's look at this example. Can we reach the last position or not, right? That's the question we are trying to answer. Let's brute force this. How can you brute force this problem?
Or let's think that if we are at index 0, we have 3 options. We take the max of these 3 numbers and then move ahead. And then take max of these 2 numbers and then move ahead till we reach a point because in worst case we'll run this loop n-1 times. So run this loop n-1 times and at the end check if our iterator or iterator is at n-1 or not. If it is at n-1, we are good. We should return true. If we are not at n-1, return false. But let's see.
Well, let's look at every possible path we could take. So remember, we start over here. What's every single path we could take that could potentially get us to the end? If we know that 3 is at index 0, this is index 1, 2, 3, and 4. So these are the indices. So I'm going to start at position 0, right? We're starting at position 0 and see the value we have. The value we have is 3. That means we can make a jump of length 1. We get to index jump of length 3. Going through all this work because we're jumps, right? A jump of 1, take a jump of length 2, repeated work length of I'm going to show you how to capture the solution. So from here, we get to index 3 0 dead end. You go through the rest. This 3 is also 0. If we were doing the brute force solution, right, which is what we've been doing up until now, creating the entire decision tree, what would we do now? We would continue the brute force, right? We'd see, okay, at index 2, we have a value 1. That means we can make a jump of 1, right? And when we make that jump of 1, we get to a 3, right? We get to a 3, and we know 3s are dead ends for us, right? We cannot continue with 3 anymore, right? This is what we would do if we were doing the brute force. I'd continue, doing this part. But notice we don't actually have to do that because this is not the first 2 that we have encountered. We've already visited index 2 before. Right? Look over here, right? Here we visited index 2. And what we can do, and what we found was we actually reached the base case for that. We found that this was a trap, right? We could not reach the last index when we started at index 2, right? That's what this diagram, this decision tree tells us. When we start at index 2, we cannot reach the end. We get stuck at 3. So what we can do in our memory is dp, let's say we have an array called dp, right? That's going to be our cache, dp of, and it's false because we could not reach the end. So now when we're over here in this position, index 2, we don't have to do anything, right? We don't have to continue that decision of making a jump of 1 and then getting to 3. We can actually immediately stop this, say, okay, no, we know that from here we cannot cannot reach the end. And you know what you might have noticed by now is none of these paths can reach the end, right? So if we were doing the DP solution or a cache, or rather this one, right? This tells us we're at index 1. The root of this, the root tells us when we started at the first position, right? That's basic hash. You can get this solution to be O of n squared time complexity, but there's actually an even better solution. We can be greedy and we can get a linear time solution, a big O n solution. Let me show you how to quickly do that. And then the code is actually pretty short. Let's take a look. Okay, so now let's get into the actual greedy solution. So this is greedy and it's going to be linear time complexity. This problem has a pretty simple solution. We don't actually need dynamic programming. Let's look at we know that this is the starting position, right? The left or the first index is the starting position. Our goal is to get to the end position, right? But let's actually look at this in reverse order. Let's start at the end position and then see if we can work our way to the beginning in a sense, right? So in actuality, the first index is the starting position. This is the goalpost, right? This is the position that we're trying to reach. But we can see, let's work our way backwards. Let's take a look at this position. It's right next to the goal, right? This is our goal, and we're just pretend like this is a goal. So this is our goal, and this is right next to the goal. 1 means that we can make a jump of length 1. So really, we go here, we make the jump, and now we're at the goal. What does that tell us? Doesn't that tell us that we don't actually need to reach this position anymore, right? If I'm starting over here.
Wait, I should just write the bottoms up as well, right? Yeah. So what's this? If it's greater than n minus 1 or n, return true. So dp of n minus 1 will be set to true. That's it, right? And from n minus 1, here we return dp of 0 for n pi equal to n minus 1, or should we say n minus 2, I is greater than equal to 0, I minus minus for j equal to I plus 1, for int j equal to I minus 1, j is greater than equal to this still will be like this. J is greater than equal to max j plus plus. What is max? Int max equal to math dot max n minus 1 and I plus nums of I. Right now, what do we check? If dp of j is true, then return true. Can reach subject to false. Right. This would mean that dp of I is set to true. And reach is set to true as well. If can reach is false, not just dp of I equal to can reach. Yeah. What? Oh, this will be minimum. My bad. Okay. Let's see. So, oh, okay, click pass. But should I submit it? Let's ask first. This pass all the range test cases and the code. Let's go. Still pretty slow. Why? I mean, it is a open square solution. Okay, but still tabulation.
Right? Let's say we're starting over here. This guy over here can literally reach the end position, right? We know for a fact this guy can reach the end position which we're trying to reach. Doesn't that mean that we can take our goalpost?
Okay, we can say that this and this. Wait. No. If I'm at this position, if this returns false, but if I had 2 here, this returned false, but this returned true. Let's see.
And then shift it over here, right? Because we're not trying to get here anymore. Now our new goal is to get to this position because this can reach the end position, right? So from here, we're now trying to get to this position. We move the goalpost a little bit closer to us. So now we're gonna put that goalpost over here. So now let's look at the next position in reverse order. So this is also a 1. That's good for us because we can make a jump of length 1 over here, right? Now notice this guy can't reach the end position, right? Which is bad, but it can reach this position, which is where our goalpost is, which is all that really matters, right? As long as we can reach the goalpost, we can keep shifting it. So now let's shift the goalpost one more time. We can move it just a little bit closer to our initial position. Now we work our way backwards again. We're at a 3. That tells us we can make a jump of length 3 or less. So it could jump 1, 2, 3 all the way over here, right? That 3 could jump all the way to the end, which is awesome for us, but that's actually unnecessary because we see the goalpost is even closer than we expected. Now it's over here. So it can make a jump of 3 or it can make a jump of length 1. It makes no difference because either way, we can now take that goalpost and keep shifting it. So now the goalpost is over here. We're almost done with this problem. Now we see we're at 2. We can make a jump of length 2 or 1, and then we reach here, right? We reach the goalpost from the first position, right? Therefore, we're moving it one last time to the start position. What that tells us is, yes, we can return true because from the starting position all the way at the left, we are able to reach that end position, right? We're able to reach the last position. So we return true. And we did this in linear time because we were greedy. We kept shifting that goal. A big old decision trap. It's pretty simple. So the only end, so it's going to be the end, right? So either two things will be true. Either goal will now be 0, right? Meaning that from position 0, we're able to reach the goal, or goal will be greater than 0, which means we were not able to reach the end of the input list. So we can make a condition to return that. So return true, goal is equal to 0, else return false.
Okay.
So this is how you solve jump game in linear time with the greedy solution. No extra memory is required, and this is how you do it in Python. In Java or C, it might just be 1 or 2 lines of extra code, but the general solution is the same. So hopefully you are able to code it up, and I hope that this was helpful. If it was, please like and subscribe. It supports the channel a lot, and I'll
We have our int goal, which is n-1. Now, for int I equal to 0, I less than n I plus plus. Now, we start from n-1 and move up to 0. This is minus minus. If I plus nums of I is greater than or equal to our goal, then set our goal equal to I. Yeah, that does make sense. Then return if goal equal to 0, return true, else returns false. Okay, this is that optimal solution of an solution, right? Greedy. Okay. Nice. I will be back soon. I need to go to the washroom and I will be back soon. Jump game 2.
₹9 cannot even buy you a cigarette.
Hey everyone, welcome
which
back.
kills
Let's
you.
write some more neat code today. So today let's solve jump game 2. So you might remember recently we solved the first jump game problem, and I would recommend watching that video or solving that problem yourself before looking at this one, because this one is actually...
Have I solved unique paths? I guess I have, right? Yeah, I have solved unique paths 1 as well as 2.
Very similar. The main difference is the premise of the problem is the exact same. We're given an integer array of non-negative integers. They're always non-negative, and we are placed at the first index of this array. So let's say this is our input array. We're going to be placed at the first and jump to the last position.
Each in the recursive mechanism is to reach in the minimum number of jumps. You can assume that I will reach the last index. Jump. We have 3, 4, and 5, 6, 7, up to 9. Okay. Jump game 2 is 45, jump game is 55. How does that make sense? Okay. Wait. What? They have modified this question. Okay, anyways. I will be back soon. Till then, fade to black. Okay. Let's solve this problem. You are given a zero indexed array of integers, nums of length n. This each element given as an element. If you are right, you can jump to any index I plus j, where j is this and this, and return the minimum number of jumps to reach the index n minus 1. The test cases are generated such that you can reach index n minus 1. Okay, so we need to find the minimum number of jumps. Again, I can use the same code. Where is jumping one? Oh, wait. Wait a minute. Yeah, okay. I need that code with the memoized code. Yes. You should just copy this part and then this part. Okay. So we can for sure reach n minus 1 if this is equal to n minus 1, return 1. Now we need the minimum value, right? So int min integer dot max value okay, so from here I make a jump min equal to math dot min of um min and this is jump of nums and j. At the end just return min and this will be 1 plus. Yeah. Mhm. Oh, what? Is this wrong? Should we return? Yeah, I thought of that. To return 0. Oh, and I don't store this here. Yeah. Yeah. Okay. That's it, right? Okay, if this is not equal to hmm. How would this ever be equal to this integer dot max value? Oh, this will. Oh my bad. The 1 plus should be in here. Yeah. Hmm. Okay. Okay. Okay, let's write the tabulation code now. Cycle count is 212, right? Let's see. Okay. Pp of n minus 1 is equal to zero. Okay. For n I equal to n minus 1, I is greater than equal to 0, I minus minus. What do we do? We run another for loop int I equal to j equal to I plus 1, j less than equal to the max value j plus plus, int max equal to max dot n minus 1, and I plus nums of I. Just copy this line. Okay. Just copy this as well. And now let's think about it. Well, this will be dp of j. If this is true, then do this. Otherwise, at the end, just store dp of I equal to the minimum value. And dp of 0 will return the actual answer.
Hi, glad to meet.
Hi there.
Hi there.
Hello. It's love.
Hi there. Hi, glad to meet.
Hi there. Nice to meet you. I'm excited to help you get things done.
Yeah, donate this. Wait, what? So, this is not me, okay? This will be dp of I. This will be dp of I. So we donate this. Next is just dp of j. Oh, we also need to check if this is if dp of j is not equal to integer dot max value. Yeah. Okay, better. Better. Tabulation. Okay, so this is working. Okay, better. Better. Yeah.
From the first position in our integer array. In this problem, though, the question we're trying to answer is, what is the minimum?
You know what? I have to say this. I just remembered where is Papa. It So my cycle count is 212. Do you know what this is? This is a palindrome. Never mind. Okay, context for that, saying that I have been solving a lot of palindrome problems. You cannot blame me. You can watch my previous streams. Wait, again? Oh yeah, this is a annoying problem. No. No thanks. What? Let's just check it here. My 100 days batch has not been updated yet, by the way. Yeah, great. Anyways, let's just solve this. Let's see its greedy approach. Okay.
Number of jumps that it takes for us to reach the last index. And luckily for us, we can always assume that we're always going to be able to reach that last index. So in this first problem, we know that we're starting here, right, in this 2 position. If we take, so since we're at the position 2, we have 2 choices, right? We can either take a jump of length 1, or we can take a jump of length 2. Our choices are these 2 values, the 3 and the 1. If we reach the 1, then we take one more jump, get to the second one, and then we take a third jump to get to the 4, which is the goal, right? The goal is the 4, the last position.
Check out the difference between this same sentence being dictated into Siri
of the array. Or if we go to the 3 instead, then we can actually just take a jump of length 3 to get to the 4, which means that in this case, it'll take us exactly 2 jumps, right? We go from 2 to 3, and then we get to the goal. So that took 2 steps, 2 jumps, and our output can be 2 because we're looking for that minimum number of steps. So you might know that this is a problem that can be solved with dynamic programming, just like the first Jump Game solution. But I'm not really going to go over the dynamic programming solution because actually, just like Jump Game 1, this problem also has a greedy solution, and it turns out that the greedy solution is a linear time solution, so big O of n, whereas the dynamic programming solution is actually big O of n squared. So we know that with this problem, we can make some kind of decision tree, right? We know that this first position, right, 2, it has 2 choices, right? If we're jumping from this position, right, we can jump to the 3 or we can jump to the 1, right? So those are our decisions, right? So really from 2, we can get to these next 2 values. The greedy solution is going to be something similar to a breadth first search type solution, right? So we looked at this value, right? This 2, that was the starting position, and we saw that these are the next values that we can go to from there, right? We're going to continue this process. That's why it's kind of like a breadth first search, because we're going to be continuing this exact algorithm. What we're going to be doing though now is we saw that from here, we could get to these next 2 values. Now the next question becomes, from this entire portion of the array, what are all the other values outside of this portion that we can also reach? Let's take a look at that. From this 3, we know we can reach this next one, right? But that doesn't count because it's already a part of our green area, right? We can reach that one, but it's redundant because we can already get to this part. We can also get to this next one, right? So that's going to be at the next level or the next part of our breadth first search. We can also reach the destination, which is 4, right? At this point, we would normally be done with our algorithm because we know that we can reach this 4 and we've basically found the minimum number of steps that allow us to do that. But we're going to continue with this just to understand the algorithm. So we know that from this 3, we are able to reach these 2 values. Let's just continue it just to see, okay, this 1, we also need to check what are all the positions it can reach. Well, in this case, it can only reach this one, and that's already included in our purple area. Okay, so now we see that this purple level is what we can reach from the green level, these portions. And the whole reason I'm color coding this is because the levels tell us how many steps it takes to reach these cells, the minimum number of steps, right? We know that we start at this position, right? Therefore, the number of steps it takes to reach this position is 0, right? It takes 0 jumps for us to reach this position. Now my question to you is how many jumps does it take to reach the green values? It takes exactly 1 jump, right? That's the whole point of color coding it, because we know from 2, we can jump here or we can jump here. It takes 1 jump for us to reach any of these values if we're taking the minimum route, right? We're taking the minimum number of jumps. Now, next, what about the purple values? How many jumps, what's the minimum number of jumps that it takes for us to reach these? Well, obviously it's 2, because if it takes us 1 jump to reach these green values, and we can take 1 jump from the green to get to the purple, it's going to take 1 extra jump to get here. So it's obviously going to be 2 jumps. jumps, right? This is pretty simple. This is a pretty straightforward algorithm. We would continue it if we had more values in our array. But as you can see, what we're doing here is basically through a simple or a one-dimensional array breadth first search, we are finding the minimum path or the minimum number of jumps to reach the destination, right? Remember, we only care about the destination. Once we reach the destination, we are done. So in this case, we can see it takes exactly has two choices, right? If we're jumping 2 jumps for us to reach the destination. So this is the visual explanation, but now hopefully you get the idea of what we're doing. The colors hopefully can illustrate that. Now the breadth first search algorithm. I'm also going to have 2 pointers, left and right, and they're both initially going to be set to 0 because these left and right pointers are going to tell us our window. We saw that initially the window starts at just 0, 0, right? The first initial value, so that's what it's going to be. We know that, I think the second level was where left equals 1, right equals 2, right? So this would represent a window from index 1 all the way to index 2, and this is basically going to determine what level of, or what portion of the array is going to be used for breadth first search currently. And we know we are going to continue this algorithm until right, which is the rightmost value of our current portion, until it reaches the last value of the input array. So while our right pointer is less than the last index, we're going to be continuing our algorithm and keep incrementing that result. So just for visual purposes, what I mean by the left pointer is that, let's say, so that's great. Last thing is, how are we going to determine the boundaries for the next portion? Well, what we're going to do is we're going to look at who can jump the farthest. The 3, the farthest jump it can make is 1, 2, 3, right? The farthest jump it can make is to this value. The 1, the farthest jump it can do is just a 1, so it can get here. It's going to be adjacent to the right pointer. So this is where our left pointer would go. Where's our right pointer going to go? It's going to be adjacent to do now to update our pointers is we're going to take our left pointer and set it to right plus 1, right? It's going to be adjacent to the right pointer. So this is where our left pointer would go. Where's our right pointer going to go? It's going to go to the place that we can jump the farthest, right? It's going to go to the right boundary of our purple area. So we're going to cross this out and put right over here. The reason we're putting over here is that's the farthest position that we can jump to from the previous section, the green section. So now let's get back into the code. So we are going to have a variable farthest, which is going to tell us who can jump the farthest and what from jump the itself. Index I, so I plus end of it, we should be good. Far to right plus the entire, it's in the input array. That's when you know that we're done counting the jumps and we can stop our loop, and then we can return the number of jumps that we took, the minimum number of jumps. So I hope that this was helpful. I hope you have a visual understanding of this problem as well as understanding the code. And thank you for watching. Don't forget to like and subscribe if this was helpful, and have a great day. I'll see you pretty soon.
Okay, let's see this problem. Best time to buy and sell stocks with cooldown. Should I go for jump game 3? Should I do it? I should solve these, right? I should. Okay, let's do it. Given an array of non-negative integers ARR, you are initially positioned at start index. When at index I, you can jump, or reach any index. Check if you can reach any index with value 0. You cannot jump outside. Okay. All possible ways to reach. Given an array positioned at start index of the array. When you are at index I, you can jump to I plus array, or check if you can reach any index. Oh, with value 0. Okay. Okay, so first we need to find the end position, right? That is our 0, where our 0 is. So we'll run a loop just to find the 0. And we'll and we have to store all the zeros, indexes of all the zeros. Right. Hmm. Okay. I will be back. This is not a 1300 or a 1400 rated problem. This is quite a difficult problem. Yeah. Mm. What is the rating for this problem? 1500. Maximum number of jumps to reach the last index. Any index j such that j is always greater than I and within bounds, and nums of j minus nums of I is between negative target and +10,000. Okay. And this cannot be of n square solution. Oh wait, I can't do a open square solution. And I have to be careful because I have to use long. While computing. Okay. Okay. We will solve these problems. But first, I need to go to the temple. I will be back soon. Till then, fake to black. Elijah's kiss coming. Elijah's kiss coming. Let's see. Master guy. Oh my god. My streams are okay. Okay, anyways, let's just move on. You are given 0 indexes. They should be within this range. Hmm. You are given index 0 and 1 step from index I to any index j to any index j. To any such that j should be obviously greater than this, but it should fit in this range. Okay. That was close. Int n public int. Let's call this strings. Int nums. Int target. Int I. Okay, so this dot n equal to nums dot length. Return jumps. Nums target start from 0. If I equal to n minus 1, return 0 because we don't need any more jumps. Right now. Or int j equal to I plus 1. J is less than n. J plus plus we just need to check if nums let's call this diff if difference of nums of j, we are not adding anything, right? We are just checking the difference, so we should be good by using int nums of I. Oh, the numbers can be negative. Okay. So if difference is within the range target and difference is unequal to it. If this is true, then move ahead. Then move ahead. Nums target and this will be j because you are at that index and from this index you need to find how many jumps you can make till you reach the desired what do you call it? Desired index, which is the last index. Okay. Right. And you need to return the max. Return the maximum number of jumps you can make. Int max equal to 0. This will be 0. I've learned from a mistake. Yeah. Let's go. Oh, expected -1. Why set -1? If there is no way to reach n-1, return -1. Target. mm, else else max will be set to -1. Let's see. Now this is wrong. This is, yeah, I don't think this is the right. Should I do this integer dot min value? If this returns integer dot min value, wait, this needs to be long, right? Then return -1, else return this result. No. Why is this solution wrong? Set. Just a minute. Okay. It's conceptually close, but this is because it recomputes states and this causes TLA and can also take in of this. What's wrong with the expansion? I will memorize the code, but just tell me. Yeah, that's why I was starting from 0. How do I find this unreachable state then? Int max is -1. If this, then find next. Okay. So this will be -1. And then when we are in here, so yeah, int this will be long, or should I long next? It suffices an int. Okay. Int next. Just call this chunks. If next is not equal to -1, then update max. Otherwise, we are good. And yeah, that's it, right? Yeah, it should be good. Okay. Okay, I need to memorize this code. We only have one state that is changing. So we should be fine. And if dp of I is not equal to -1, return dp of I. Before returning, just store this here. Yeah, that's it, right? Oh, wow. I was thinking, should I store this as well? Should I store this as well? Yeah, that doesn't. You only have one state. Oh, interesting. I never initial that was okay. Great. Great work. Just thinking. Oh, safety. Can take this in pass. Wait this pass on the test. Six one eight. Well, extend. Why did I get that clearly on this test case? Because I should try more clearly. Yeah. Okay. Wait. We should use integers then. Right. So if this is null, is not null, then return this. Yeah, we should be good now, right? We should be good. Yep. Nice. Should I also write the bottom sub approach? Yeah. I should write memoization. Okay, great. Get out, commit. This is this. Using ization. Get and nice. Yeah, anyways, let's convert this into okay. So first of all, initialize PPO JP of n minus 1 equal to 0. So we start from n minus 2. I greater than equal to 0. I plus plus. Now just just copy paste. Now this is minus 1. Correct. This will be dp of j. So now instead of doing this, dp of 5 and this will be this will be int that is will dp with minus 1, and if this is minus 1, then this okay. Okay, we should be good. Oh yeah, just comment this out. dp of 5. Yeah, yeah. Great, we have out of bounds condition. Now we have out of bounds condition. What? How do I have out of bounds error? Error. Is giving same error. It's a runtime error. What? And can never be equal to 0. Hmm. Oh, uh, oh, come on. Oh, okay, that's not wrong. Nice. Okay, this should run exactly often scratch times. Yes, it is faster. It is very faster. Calculation. Connect. This using tabulation. Git push. Now let's solve this. 308 only out of 3,700. Given an array of non-negative integers, you are initially positioned at start. Yeah, and okay. You can move forward and backwards this many amounts of times. Check if you can reach any index with value 0. This dot n equal to arr dot length and then now we know the start. We want to go to the end, right? So we create a hash set. Let's do it. Hash set integers set. But this is basically the zeros alias equal to new hash set or int I equal to 0 I less than n I plus plus. What should we do? We should if arr of I equal to 0, then set dot add I. That's it. So now we have the start index, we have the end index. Let's do this return jump. What will this say? We'll insert the array, the start index. Public boolean jump int arr int I. That's it. If zero index right contains I, if this is true, then just return true. Now, if it does not contain zero, at that it's we have two options. Either we go left or we go front. First, let's check we are within bounds or not. If I is less greater than equal to 0 and I is less than 10. Oh wait, if we want to check the condition for out of bounds, right? If this is less than 0 or this is greater than equal to n, then return false because we have not reached that index which contains a 0. Now we have two choices. Int right, this will be boolean jump arr I plus arr of I and boolean left jump arr oops I arr I. Now return right, oops, return left or right. If either one of them returns true, then there is a possibility to return true. That's it, right? Oh, yeah. We're not doing all this stuff. How? Okay, even if this is going out of bounds, we are checking that we are within bounds, right? You know what? We'll never go out of bounds. String 0, 1, 2. First, let's just check why this is wrong. Why is this wrong? Oh, my bad, my bad, my bad, my bad. I, yeah, of course. It, of course. This condition or this condition is going to be true. It's never going to happen that both of them are going to be true at the same time. We need to keep track of physical as well. Why did you keep a track of physical as well? Hmm. Hmm. हो, जेवतोय. मग भात एवढा नको मी कमी करतो. काढून ठेवतो. Okay. Okay, so when we leave, okay, I have it out. Let me pull it up and then let's see. I thought there can be multiple zeros, so whichever reaches first, we can we can do. But yeah, it doesn't need that. ARR of I equal to 0, then return true if physical physical of I equal to true. Boolean physical of size, and this makes sense. Okay. Yeah, but what if I do this? While I backtrack, I need to set physical to false, right? Is this correct? Code will fix all this. Let's see. This break cycle prevention. Okay, so once mark visited, you can never visit out again. Okay. And yeah, I also need to do I need to memorize it? Yes, no, right? Do I need to memorize this code? I don't think so because we are literally visiting every single index is just once. Yeah. And either index I can read 0 or I cannot. Mm, so never changes. Yes. Yeah, this is basically O of n solution. Yeah, let's submit this. Perfect. How's this here? Should I write the top down? I should, right? I will write the top down approach as well. Three. Where is this? Oh, okay. This is memorization. And connect using memorization. Get push. Okay, that's it. I'll be back. Wait, I will be back soon. I need to eat first, then I'll be back. Till then, fake to black. Okay, I'm back. Let's solve this problem. Okay, so what I was going to do is write the tabulation form for this code. Okay, so what is this? If we are out of bounds, return false. If array of I equal to 0, return true. If that is already visited, return false. Hmm. For int I equal to let's start from here and then I plus plus Uh,
हाँ आई बढ़िया हाँ हाँ उदय ना हाँ हाँ संडे बनून
Okay. Yo, what is this? Alright. Now, if this wait, if array of I equal to 0. Okay. Okay, this is not a TP solution. This is a recursion. So so I can never have the calculation because I have never memorized the code. I calculate this. Ekte. Nej. I mean, I have to check this as well, right? For right. I need to check. Let's see. माहित नाही बघू इथे झोपेन इथे झोपेन दादी तिथे झोपतोय ना
जागा आहे ना
Okay, so I know there are two ways to handle this. Either by doing this. Oh, yeah. We are off by one. Okay. Oh, wait. Yeah. So I just did a -1 here. Easy fruits. So like if 1 plus 1, 1 plus this is ever becomes equal to this. Yeah, then you, you are basically equal to integer dot max value here. Okay, anyways. Mm, hmm. Or should I just not even execute if this if if this is equal to integer dot max value, just don't even execute. Right? That part. Yeah. Uh-huh. Let's do that instead. If y is not equal to this, then calculate right equal to min equal to math dot min of min and right. Now, same goes for left. This will be minus by the this, this, and this will be left. Yeah. Mm, continue. If it's returning integer dot max value, it means it is invalid, right? So why do you want to do that? But if I just remove visited, let's see what happens. So this is necessary. Okay, let's see. Why am I wrong? Where am I wrong? Why am I wrong? Except this is problem number 24. You're using recursive PFS with backtracking. This draw asks for minimum number of lines the shortest problem on an indicator. Yeah. Let's visit it. I mean, I will obviously. Memorize this. Oh, even so, offense were won't at all. Oh, yeah. Forgot about that. Yeah. So still, why is it wrong? Don't want to do a PFS. Yeah, this is cycle bar. Yeah, that's what I am doing currently. Why? While backtracking, I second the force. Why? Why do I do that? Visited my political force. This is so stupid. I don't understand this. Here, while backtracking, we mark the cells unvisited. Why do we mark the cells unvisited once we have uh, no, while backtracking? Now, what was that previous problem? Yeah, in jump game 3, why did we never backtrack then? This is realizing remains to know. Okay, so when we do this, we are saying I'm done extraction parts that go through I and then I mean the same activity using different path execution for a possible combination. is correct when you need to explore all paths. You're solving existence/enumeration problems. Just a bit. Here, in shortest path problems to this node is already finalized. This is insane. So I cannot do a DFS here. Okay, so I have to write a poll with PFS, which uses PFS public and jumps. Now, what are the things I need to write a BFS code? I know one is a visited Boolean array. Uh, we have a visited Boolean array. We have a queue, and that's it, right? And we run the loop until queue is empty. Yeah, I nothing else is needed, probably not. Value to basis. This is a correct code, but what should we make here? We have to do this. Int in wait, do we need this? hash map. Let's just send it here. Hash map integer and list of integer. This is our map. New hash map integer. Oh, I don't need to make this. Okay, now let's compute our map. Map dot if absent. What do we have? Array of I and new array list, and also add at this index add I. Am I gonna this if n is less than equal to 1, return 0. Okay. Yeah. If no, let's not check this first. Let's see what happens, right? Okay, we have this. What do we want now? We need to send the array list. We need to send our hash map. That's it. Return jumps here are now. Start from the 0th index. Boolean visiting equals to new Boolean of size n. Let's just keep this as a global variable. This n. Okay. Now we have a visited bakery q integer. Okay. Int steps equal to 0. Now we just add into our queue, right? Queue dot add add error of 0 visiting of 0 equal to true. So this index is visited and we only need the index of this. What does the function do in Java? Select. Oh, I need to charge Laptop in charge. Oh yeah, Q. Sorry. Is used such as insertion. Also remove element y the most so why are we using offer like we are removing things here? Okay, we are adding things, not removing them. Yeah, got it. Because I never saw them using poll. Yeah, they used it here. Okay, so while yeah, while Q is not empty, int n int n equal to what is this? Q dot size. So while n oops, is greater than 0, what should we do? First of all, remove that index. Then once we have that index, what do we do? Yeah. Check the very first base condition. If this is equal, return steps. If not, steps plus plus. If I minus 1 is greater than equal to 0 and if it is not already visited, then you have to mark this as visited first, right? Oh no, we mark this. As soon as we add it in our queue, 2 dot offer I minus 1. If I plus 1 less than array dot length, and this is also not visited. Do this. Okay. Now the special case. If map dot contains key array of I, then for every int j in map dot set or what is map dot get I for every element in that, I mean every index array of I, right? So it's to be array of I, yeah. What do? We mark this as visited and add it to our queue of our, yeah. Yeah, so we need to handle for this case. If n is less than this, then return 0. Yeah. Wait, why is this wrong now? Everything was correct, right? Wait. Yeah, let's name this as size. Oops. Okay. This dot n int n. Then just keep this as n. If I equal to photo n minus 1, return steps. or return -1, but this will never execute. What is wrong? Let's go 3, 24. It's counting a lot of steps. Oh wait, ah, yeah, this makes sense. Oh yeah, and this should not be visible as well. Yeah, it will never this point, right? Hmm. Why is this optimal? Because we'll never encounter this again, right? Otherwise, remove array of I and not this is I'm good with all the anyways. Yeah, we should remove this. This is important here. Map dot remove array of I. This was a good problem. Yeah. Yeah. Oh, what? Jump 5 is easier than jump 4. Like, according to the acceptance rate. What is this? $1866. Okay, what is this? Given an array of integers AR and an integer K. In one step, you can jump from index I to index I plus x, where I plus x is less than array of 10th, and x is between 0 and d. I minus x, where I minus x is greater than equal to 0, and x is within the 0 and d. In addition, you can only jump from index I to index j if array of I is greater than array of j and array of I is greater than array of k. You can only jump from index I to index j if array of I is greater than array of j and array of I is greater than between I and j formulae. Okay. You can choose any index of the array. Okay, and start jumping. Return the maximum number of indices you can visit. Notice that you cannot jump outside of the array at any time. Okay, this is a good problem. I need to take some break. I will be back soon. Till then, fade to black. Okay, let's go. This looks like a big problem. Not gonna lie. Let's search it on YouTube.
So you want to be a
So you just mentioned.
Hello, this is the fourth problem of LeetCode Weekly Contest 174. The name of the problem is Jump Game 5. So here we are given a question that in an array there are certain values and we are also given a value d. So basically we can make our jumps in such a way that if suppose if we are at an index I, so we can make our jumps to I plus x such that x is smaller than equals to d. So for example, if we are at an index say 5 and d is given as 2, so we can make jumps from this position to 2 positions to the right and 2 positions to the left. Also there is another condition that if we make jump from a particular index I to either to the right side or to the left side, then the values falling on the left should be smaller than I, and the values falling on the right should be smaller than the value at I. Should be smaller than I, and the values falling on the right should be smaller than the value at I. So for example, if we are at an index, suppose if we are at 5th index and if d, so for example, and to the right side, that if we make 2 positions to the left. Also there is another condition that if we make jump from a particular index I to either to the right side or to the left side, then the values falling on the left should be smaller than I, and the values falling on the right should be smaller than the value at I. So for example, if we are at an index, suppose if we are at 5th index, and or we can jump here and we can jump here, or we can jump directly to this point. Now what we cannot do is, suppose we are at this index 4, so we can jump to the left side because left side is smaller than this, left side is smaller than the current height, but we cannot make a jump to the right because the right side, the height is greater than that of the current height. So if the question is clear, it is very easy to implement it, as it is a recursive problem and we have to do exactly what the question says. So what we are going to do is, we are going to start from every index and then try to go right and left as stated in the problem statement. So for example, if we are starting from an index I, and we will start actually from each and every index. So suppose we are starting from an index I, so we will try to move to all the positions from I plus 1 to I plus x.
I plus x, yeah. I plus 1 to I plus x. Oh. Yeah, okay. So basically less than equal to I plus t.
And from I minus 1 to I minus x. Of course these values, they should lie within the range of the array. So this should be greater than equals to 0 and this should be smaller than equals to n minus 1, where n is the size of the array. Now we can try to code this problem in a recursive manner. So for this, and n is right side, I plus 1, minimum of I plus d, comma n minus 1, because we should not exceed the limit of the array. Now there is another condition which we have to handle, that array of I, this should be greater than array of j. So as soon as we come to an index which is greater than or equals to the current index from which we are going to jump, we should break this loop. Your answer is equals to answer maximum of answer comma. We will again call this function. Here we are passing j as a parameter because now we are at an index j. Now similarly we will go to the left side. Here we will start from I minus 1 and j is greater than equals to 0 and I minus d array of I. Now we need to return answer.
Okay. Is it, what? It's that easy. Okay, you just need to check two conditions and we are good.
With 95% of the companies going multi.
By the way, why did you set answer equal to 1? It should be 0, right?
Here also we are initializing answer, and we will try to start from every index. So answer is equals to maximum of I. This showing a heap of overflow. This is actually maximum.
Oh. Hmm. Yeah, that's what I was thinking. Why didn't he add a +1 more? But yeah, okay. Correct something.
It is giving us the correct answer. Okay, so the time limit got exceeded. So now we need to optimize this approach further.
Memorize it.
So for the optimization here, we can have a look at, suppose we are trying to find the answer for index 8 and we successfully did that. So the answer for index 8 is, the answer for index 8 is second index. So for, let's say, 8th index, complexity of the solution, DP array. We make 2 jumps.
Yeah, this is easy, but okay, I get it. Okay. Int n int p is going to be single state. Public int jumps int array int p and int I. Int this dot n equal to array dot length. Now for int I equal to 0 is then n time I plus plus. Try for alright int once or result equal to 0. That's what I think. Max dot max of result comma jumps from this. Before doing that, every single time, just reset our TP array. At the end, return our result. Int TP equal to new. This will be of size n. Now, int result equal to 0. Yeah. For int I equal int j equal to I, right? J is less than equal to I j plus I. Let's just call it I. A is less than this, and this is within bounds. Oh wait, this should be math dot minimum of this will be I plus k and n minus 1 j plus plus. Right, j should be less than from I to till I plus k, and it should be within limits. So this will be, yeah, and array of I should be greater than array of j. If this is true, then result equal to math dot, we need to maximize it. So max of result and 1 plus jumps of I d. Now we send j. So this will be from I plus 1, right? Yeah, perfect. So for j equal to I minus 1, this will be 1. This and this. One result. Is it off by 1 year? Because it should be this. Yes. Yeah, I thought of it, but I was like, probably not. Okay, yeah. That's why I guess he started from 1, but no, I don't think so. I don't know. Nah, whatever. Anyways, this will give a TLA, obviously, so let's just memorize this. If kp of I is not equal to minus 1, check that. Otherwise, kp of I equal to this. Oops. Okay. Let's see. Yeah. This was then this. Like the time complexity here is O of n square. Why? Because we are recursively calling this function once, and inside this recursive function we are running this for loop and again this for loop. Basically we can call this as O of n times 2n time complexity, but 2n is basically O of n, which means this is O of n square. Okay, now let's see. Wait, what? Wait. We don't do this like every single time. Count current index. Okay. Okay. Okay, I get it. But why should we set this equal to 1 for y result equal to 1 for trace one jump count by standing on the current indexes? What you stupid. So you can make a jump on yourself. So don't want. Okay, let's add an element, like a single element. Oops. Let's run this. No. Yeah, this is correct. This is correct. Let's submit. Perfect. Okay. This was actually pretty easy question. I'm gonna lie. Take. I can also memorize the code, right? I will memorize the code. I mean, write the tabulation or the bottoms up code as well. Okay, let's write the tabulation code as well. In AP, this is this. Okay, for int I equal to 0, I list n plus plus. This is O of n cube solution, by the way. Check it. O of n into k. Okay. This will be direct. This will be directly of one operations. Shouldn't be O of n cube solution because once we are running this for loop, then we have our recursive call, which inside which we have another for loop O of n square, O of n so this will be O of n cube, right? Correct me if I am wrong. Okay. Hmm. 1 plus dp of j. This will be dp of j dp of I equal to result. Just do this instead. dp of I, the theta. This will return on calculation or but this. That's it, right? Hmm. Okay, it should be good. Okay, so I need to sort this now. Damn it. What? Oh, sorting dice is going crazy order. Okay. If this is positive, this is bigger than this, so small. This is equal to nothing. This is small. That's negative. Nothing. Okay. Hmm. So sort on the basis of I sort basically IDX A comma B return array of A minus array of B. Now ID IDX. So okay, this should work. Yeah, let's go. Do we even need to check this condition? No, right? Yeah, we don't even need to check this condition now because it is already sorted. God damn it. Why is it giving wrong answer now? Oh, I like this word. So this is necessary. This is necessary. Hmm.
Hello, how are you? I am good.
I should have given today's contest to I yeah. 4-4. Sure. Anyways, 6, 7, and then 9. What is this acceptance rate? 20.8%. Oh wait, what? I have tried to solve this problem. Um, is ahead. I value data. This case is invalid. Invalid. Okay, wait. I do remember this problem. This was me trying to just kind of simplify these two conditions. Operating data behind the That include this stuff. Okay. God damn it. I'm writing for loops. Right. Going 12,000 accepted out of this. This was asked in recent, yeah, contest weekly. August 24th. Yes. Oh, yeah. I mean, okay. We'll figure that problem out. But first, let's solve this problem. Jump game 6. Oh, a 9100 problem. I will come back. I need to go to the washroom. And I will be soon. Till then, fake to relax. Okay, let's look at this problem. You are given a zero index integer array nums and an integer k. You are initially standing at index 0. In one move, you can jump at most k steps forward. Okay, it's only forward without going outside the boundaries of the array. Yeah. That is, you can jump from index I to any index in the range, this to this inclusive. You want to reach the last index of the array. Your score is the sum of all nums of j. Where they want to maximize the score. Okay. And jumping k steps forward without going outside. Okay, okay. So there are negative numbers as well. Okay. So this dot n equal to nums dot length in 10 public int jumps. We have our int nums, int k, int I. If I equal to n minus 1, you cannot have any more jumps. Right now, we start at 0. So if no, for int I equal to j equal to I, j is less than equal to math.min of n minus 1 and I plus k, j plus plus, yeah. Now, last this index, the score is the sum of all j for each. Okay, so we need to maximize this. Int score equal to 0. When you're at nums n minus 1, return nums of n minus 1 or I, whatever. Right? So, what can I do here? We have two choices, whether to take this or to not take it. Int take equal to jumps of nums k and I plus 1. But this will contribute, whoops, here. Take equal to 0, skip. Skip plus equal to, wait. Yeah. No, we are skipping, right? So this is jumps of nums k and I plus 1. Now, score will be plus equal to math dot max of take and skip. Now return score. Hey. Oh. How am I wrong here? This is 10 power 5. So DP also won't work. I have to write a DF or BFS. Wait, let's see. Why is this given wrong answer? Why is this given wrong answer? Let's say, oh, I know I'm very close to solving this problem. I'm very close. Should it be K plus K comma square? Oh wait. This should be, oh my god. this should be this I plus 1, or this should be j, this should be j. Yeah, my bad. Manually. Okay, okay, okay. This should be j plus 1. Yeah. Now why am I wrong? So, using, yeah, don't memorize. What is wrong in my world? Ooh. Yeah. No, no. I have to move ahead, right? I have to move on. Like, wait. So should this be numbers of j then? Oh, that's what. Yeah. J dot and body. we can either jump to that index or not jump to that index. So we have a choice, right? Array. So why not do using my method? Every index change I jump to or skip it. Yes. This value you must make exactly one jump. One index. Index must be in this. All other indices are irrelevant. Okay, we don't need this skip because we are all because we are moving on as well, right? Like this is obviously going to increment. So score equal to math dot max of score and this. But obviously this won't work because constraints are high anyways. Yeah. Even if I memorize this code, it's 10 power 5, so it's obviously not going to work. So I need to write a BFS code. Public int BFS. We need int nums, int k, and that's it. We have int n equal to nums dot length boolean physical array new boolean of size n. Now we create a queue of the data type integer new linked list u dot add nums of no 0. We store the index here, right? And physical of 0. Set it to true. Now what do we do here? While q is not empty, we get the size q dot size while size minus minus this is greater than 0. What do we want to do? First, get this index q dot poll and check if I equal to n minus 1. If this is true, then return the score and score equal to 0. Right now, now that the base condition is handled, what do? We move from I plus 1 for int I, I equal to, j equal to I plus 1. J is less than equal to math dot minimum of n minus 1 and I plus k j plus plus. We check this condition. Score equal to math dot max of score and nums of I plus what is this? Jumpscare j. Score plus equal to nums of I q dot of j visitor j. Now I am missing something. Nums at j, right? Score equal to math dot max of nums of score comma nums of I plus nums of j. And this should not be visited again. Yeah, this condition is wrong. Let's ask this. Why is this code wrong? Okay, so attack index, what is the current score? Score. Okay, what is this? Okay, we'll solve this problem tomorrow. I need to sleep. I am tired. It's 1:50 a.m. right now. I need to sleep. Okay. My even died by the way. Okay, I am. That's good to know. Because I can check in between whether or not I'm still alive or not. Anyways, I will stream tomorrow. Tomorrow, I need to wake up early because tomorrow is Sunday and we have leak code weekly contest which I'm going to get for sure. That is if I wake up, but shortly I will wake up. Yeah, I can't believe I missed today's contest, bi-weekly contest. How did I forget? Like, I, I, hopefully this is not lagging because it's pretty annoying, not gonna lie. Yeah, it is lagging, great. I just checked. Also, my frames are dropping like crazy. Like 70.4% of my frames are dropping right now. I'm at 2500 kbps I'm sending my claims at that rate, which is very bad, by the way. Yeah. What? I just saw my CPU percentage at negative 14,299%. What does that mean? Nice. Okay. Yeah. Don't have anything else. I'm at my grandparents' house, by the way. Yeah. Okay. Till then, I will see you